Hi, it's Renata here. If it's your first time here, welcome to my channel, The Quanti Girl, where we are going to talk about some topics in applied mathematics, in pure mathematics, in quantitative finance, and in Python program because I'm a PhD in mathematics and a financial quantitative analyst, and I'm here to share with you some of my experience. So today we are going to talk about the binomial options pricing model. So we are going to talk about the theory, and after that we are going to implement it on Python. So before we start coding, we need to talk about the theory. So first of all, we need to know what is an arbitrage opportunity in our financial market. So a self-financing strategy theta is an arbitrage opportunity if it satisfies three conditions. The first condition says that the strategy theta is surely non-negative in the initial period. The second condition says that the final value of the portfolio, the value of the portfolio in the final period, has probability 1 of being non-negative, and the last condition says that the probability that the portfolio in the final period being strictly positive is strictly positive. So in words, in our financial market is arbitrage free if there is no way of making a profit in the last period without a risk or a cost in the initial period. So now that we know what is an arbitrage opportunity, we can move on the model. So we are going to consider a call option on an underlying, and we are going to call the initial price of the underlying as S0. So in each period, this underlying price will move up or down with the same probability. We are going to call the strike call option as K. So as we know, the payoff of the option in the final period will be the maximum of 0, and the difference between the initial stock price and the strike of the option. We are going to consider here that we have an initial cash in our bank account B0. So because of this, we are going to consider a risk-free rate R. So let's move on. Just to fix ideas, we are considering here that our model has only one filter period. So the binomial tree looks like the slide. In the initial period 0, we are going to have three instruments: the underlying asset, and its initial price is represented, as we said, by S0, an initial bank account B0, and the initial value of our call option C0. So one period ahead, that in our case here in this example is the final period, we have two possibilities of the movement of the instruments. So in one direction, the value of the call option will be the maximum of 0, and the up factor U multiplied by the initial stock price minus the strike call option, and in the other direction, the final value of the call option will be the maximum of 0, and the down factor multiplied by the initial stock price S0 minus the strike of our call option K. So let's move on. Now we need to use the law of one price. We are not going to talk about this law here today, but I can talk in some video in the future. But essentially, the law of one price will build a relationship between the stock price as the bank account B and the value of the option C. So with this relationship, we will have the final value of the portfolio in the last period represented as a vector of parameters alpha and beta transposed multiplied by the stock price and the bank account. And the initial value of the portfolio will be the same as the value of the call option, and it is represented by alpha times beta 0 plus beta times S0. So again, just to fix ideas here, we are going to consider that our initial bank account is just 1. So with this in mind, we have that the binomial tree looks like the tree in the screen. So we have these equations now, and with this we can move on the model. Okay, now we are going to do some mathematics manipulation here. So after isolating alpha from the call option in one direction that we are calling here the direction up, we have that alpha can be written as the way that you can see in the screen, and from the difference between the call option in the up direction minus the call option in the down direction, we can isolate beta, and we'll have that beta can be writing as the expression that you see in the screen. So now that we have alpha and beta, we can replace it in the initial expression, and we are going to define a term here that we are going to call Q, just for mathematics manipulation, and after that we will get that the initial value of the call option can be written as the expression C0 that you are seeing in the screen. So now with this expression for the call option in the initial period, it looks like an expected value, and we arrived at the shape of a binomial pricing model here with respect to a risk neutral parameter Q. Q is not a physical probability here, just to be clear. And to avoid arbitrage, we are considering here, remember that our market is free of arbitrage. We need to have that Q is strictly positive and is strictly less than 1. And it comes from the condition that the down step is strictly positive and is strictly less than 1 plus the risk-free rate R, and 1 plus the risk-free rate R is strictly less than the up step U. We are not going to derive this arbitrage inequalities here today, but I promise you that I'm going to do it in some video in the future. So let's just move on and expand our one filter period model to allow for multiple periods. So we are now expanding to allow that our model has 2 or more time periods. So doing that, we can now see our binomial tree as a graph, and each node now will be represented by I and J. We can consider it as a Cartesian representation where E is a time step from left to right in the tree, and J is a node from bottom to top in the tree. So with this in mind, we can now represent our binomial tree, our graph, uh, saying that each node in each time period as ij, uh, writing as S0, the initial stock price, multiplied by the up step u squared j, multiplied d squared I minus j. So now we have everything that you need to code these binomial options pricing model. So just keep watching the video and code with me. Welcome back. Now we are going to code the model in Python. So the first thing that you need to do is to specify the libraries that we are going to use. Actually, we are going to use here only one library, the NumPy library. So let's import it. Now we need to specify some initial parameters, some parameters in the first period of the tree, 0, and some constant parameters here. So the first one is the initial price for the underlying asset. So let's say that it is 25. Now we need to specify the strike price for our option. We are going to use here the same price as the initial stock price. So K is equal to 25.2. Now let's specify a risk-free rate. Let's put it as 2%. Okay. Now, of course, we need to tell to the model what the number of steps that our tree will have. Let's say that our tree has 3 times steps, and let's call it by n. Now, the time to maturity of our option, let's say that it is 1 year. Now the up factor, remember that the up factor is the factor that the underlying stock price moves upwards in each time period. So let's put it as 1.1. Now the down factor, let's put it as 1 divided by u. Okay, I'm not going deeper here why we are using d equal to 1 divided by u, but the only thing that you need to know today is that making d equal to 1 divided by u makes our tree a recombinant tree, and mathematically it makes our life easier. I can talk about this condition in some video in the future, but today just accept that. Now let's specify the type of our option. as we said before, we are going to consider a call option here. Okay, let's run it. And now we are ready to start to build our function, the function that will return to us the price of our option through a binomial tree. So the parameters of our function are all the parameters that we had specified here now. I just put them, all of them inside our function. Okay. First, let's define some constant terms inside our function binomial pricing. So the first term is the time increment. It's just the time to maturity of our option t divided by the number of steps of our binomial tree n. The second constant is the Q constant that we had defined in the theory part of this tutorial. I'm just writing in Python code the same expression that we have shown in the theory part. So it is the exponential of the risk-free rate times dt minus the down factor, and we need to divide this term by the up factor minus the down factor. Okay, now the last constant term, it's just the exponential of minus the risk-free rate multiplied by dt. Okay. Now we need to initialize the asset price at maturity. So let's just write it. So C is equal. Okay, what I'm going to do here is just to write in Python the expression that we found for Sij in the theory part of this tutorial. I'm just transposing it to Python code here. So it is the initial stock price as 0. Time is now, let's write the first the d factor. Okay, d has an exponent n. Okay, now let's write the u factor of Sij. It is equal to u. The exponent is 0. Okay, now we need to initialize the option value at maturity. It is just the equation for the payoff of an option. So it is the maximum of 0. The shape of the zeros array here is the number of time steps of our tree n plus 1. So we enter the maximum of zeros and C minus the strike price of our option K. Okay. Now let's go to the last step of our function. So what we need now is to walk through our binomial tree from the last node, the last time period, to the first node, the first time period 0, increment of one time step backwards. So let's just write it. We are going to use a for loop here to do it. So for the index I in the number of time steps, the final node of the tree, and to the first node of the tree 0, increment of 1 backwards. So what you need here is the cache constant time is okay. We are going to have a sum here with the two terms. The first term is the constant q multiplied by we need here to take a slice from the vector c, and this slice goes from the index 1 until the index I plus 1. Okay, and now let's write the second term of the sum. It is 1 minus q multiplied by, now we need to take the other slice of the c vector. The slice is different from this one, so what you want here is the slice that goes from the index 0 to the index I. Okay, now we need to return the first term of the vector c, and because it is the object that returns to us the price of our option through our binomial tree. So let's just return it. Okay, let's run our function, and now let's call our binomial pricing function and check that it's working. Yeah, so now we have here our price for our option object through a binomial options pricing model. So that's all for today. I really hope that you liked it, and don't forget to hit the like button and to subscribe to my channel so you can watch the next videos. So see you next time in the next video. Bye.